record it on the cloud. I don't think we're. So tomorrow we're going to have a lab over ACI 211 mixed design method. So we'll actually go in trial batch. So today we're going to design using the ACI 211 mixed design method, using, in essence, a very similar rock and sand, the numbers you got in the lab. So pretty much we're going to take our materials, put them together. So I've already showed you, with the coarse aggregate and fine aggregate, we had 3 labs to go over how to figure out gradation, unit weight, specific gravity, and absorption. And so now we're just kind of putting some of this stuff together and actually applying it to a mixed design. So this is what was previously in the lab manual. I think I changed up some of the words because they were very, very outdated. But I think that the example's fairly relevant. But in essence, there's a 4,000 PSI mix, and they have some, information about the rebar spacing, 2-inch rebar spacing for the cover. So it's supposed to be an interior beam that's 12 inches by 12 or by 20 inches. So that's the cross section, not the length. So 12 inches in depth by 20 inches in the actual width. And so it doesn't matter how necessarily long it is for a mixed design. It's just more about understanding that the cover around that is, so in essence, if you've never seen what cover is, I'll just put it on the board real quick. So this beam's supposed to be, that's trash. That's trash. There you go, I got one that's gonna work today. Again, I write like a 3rd grader, but I think that's 12 inches by 20 inches. And then what they're saying is there's rebar, there's a cover of 2 inches. Yeah. And then they didn't really tell you what's there. It could be rebar stirrup. It could be a bunch of rebar in here. We don't really know. Again, I write really bad. I apologize. May just design this next time. But the spacing between these rebar maybe 2.5 inches, but the actual part around is 2 inches. So that's kind of what they're trying to communicate there is, hey, when you pour concrete, maybe you're pouring it straight down, your forms are around, you're pouring it straight down, the concrete has to get in through the rebar. So you can't have too large of a rock size of your coarse aggregate, or you can't pour it in there. You're going to have problems. And then also, this is the stirrup spacing. So in essence, if you think about steel reinforcement, they're very long. Well, a lot of times to hold a bunch of rebar together, you're going to have stirrups that kind of tie everything together. So this may be just a kind of like almost a square, almost. They're not, they don't have actual real corners because they're bent. But it may be put together so that it all holds all the rebar together. There may be some for shear design too. But the goal is right here is we're talking about how your nominal maximum size and making sure your rebar isn't too, it's not too big. So making sure that that rock size isn't too big. So that's why that's there. And I'll actually go through in an example and kind of talk a little bit how to check some of that. And then we talked about cement. The specific gravity of cement is 3.15. So just kind of remember that. I'll try to put that on the exams. Some people just make you remember, you know, some instructors just make you memorize it. But I'll just put it on the exam. It's not that big of a deal. We're going to use a 1-inch nominal maximum size, and we'll just check it to make sure that it fits within the cover of that steel reinforcement and that spacing. And then we have the information for our coarse aggregate and our fine aggregate, the rest of it. So specific gravities, absorptions, the unit weight, and then how much moisture, how much water's contained. So that's for the rock, that's for the sand. Admixtures we're not using fly ash. ACI 211 doesn't technically have that. I'm going to go through how to modify a mixed design or how to actually use that, how to incorporate those things in a mixed design here in a minute, or here, that's next lecture, I should say. So in a couple days, we'll go over how to do that part. So let's go through the basic steps. So you're going to choose a slump. So for an interior beam, they chose a 4-inch slump, and they got that from the table 6.1. So they used this table here. There's a maximum slump and a minimum slump that's recommended by ACI 211, you know, 30 in 1991 is when they got it published. So, you know, you can go and look at an actual beam. I think they probably used a beam and a wall, said maximum of 4 inches. And then, so I put all the tables at the back. So I'll kind of move back and forth a little bit. Sorry if that will be confusing, but I just wanted all the steps here, and I'll put this on our lab, and I'll also put it in our lecture just to make sure we all kind of have the same material. But if you have the lab manual, you have most of this. It may not say step 1, but it's the same, pretty much the same material. So use a 4-inch slump target. They just grabbed it from the table, and then what they're doing here is they're checking the actual nominal maximum size. So they're saying, okay, well, what's the narrowest dimension between the forms? So the actual dimensions. So they gave us a 12-inch by 20-inch beam. So the most narrowest dimension is 12 inches. So they did 12 inches times 1/5 is 2.4. And then for 3/4, the clear space between individual reinforcement bars. So 3/4 times, and then they gave us a maximum between 2 bars of 2.5. So they did that math. And then they said, okay, well, between the forms and the reinforcements, a 2-inch cover. So times 3/4 of an inch, so that's 1.5. So you find the smallest one out of all 3 of these, and the 1.5 governs. And so since the nominal maximum size of the aggregate for number 57 is 1 inch, then a 1 inch, that'll be just fine for what we're doing. If we're using a larger aggregate size, that was, larger than 1.5, we'd have a problem. So if it was at 1.5, we'd be fine still. So 57 or 67 stone will work just fine. Step number 3, you're going to determine the water content in the air. So they don't give us air content or anything. So this is for an interior beam, so not exterior. So interior, you don't have to have air entrainment. Exterior, where it's exposed to freeze thaw, you're going to have air entrainment. So they went to 6.2 to determine water and air. So 6.2, so this is for strength. There it is. So 6.4. You know, move these around. I know I moved them around once already. We need to move them around again. So they went through and they said a 4-inch slump. Here's how much water for non-air entrained mix. 1-inch nominal maximum size. Roughly a 4-inch slump, you need 325 pounds. And then for air content, if it's non-air entrained, according to ACI 211 for this table, it would be 1.5% air. So that's exactly what they got here. So 325 pounds and 1.5 for the air. Great. So then the next step is we're going to determine the water to cement ratio based off of strength and durability. So the 2 tables that were actually out of order, we're going to go through and look at them. So our initial minimum design, just to be clear, was 4,000. So you're obviously going to always have a safety factor above 4,000. You don't want to target right at 4,000 because you're going to have lower strengths. So there was no historical data present. So if there's no historical data, then you'll have to use a safety factor of 1,200 PSI. So 520 is what they did. And they did that from this table right here. So it's 4,000 and you don't have any history data whatsoever. You have to use this. So that's how they get the 5,200. And then, so they get the 5,200. So this is the exact same equation they just pulled out of the table. 4,000 plus 1,200, 5,200. Durability requirements, again, it's an interior beam, but it is supposed to be exposed to some type of water. I didn't actually like the table they had for the example is actually a little older, but this is actually the table they have now. The one they were using is pretty outdated. So this is normally how you actually figure out your water cement ratio and stuff for what they were doing. So 0.5 with 4,000 PSI would be those minimum, the maximum requirement for the water cement, and 4,000 for your PSI. So since we're designing for 5,200, you know, we'd still be fine. And we're designing well above that. The 4,000 was already required in our design, so we're great. We don't have any sulfate issues, and we don't have any freeze thaw issues or any chlorides, so we don't have to think about those other 3 design criteria. So mainly just doing the water, because that's what the example showed. So whenever they did that, whenever I did it, it's a 0.5 is what was actually for the durability. But when you actually go in and look at the water cement ratio using F prime C of 5,200,
you can interpolate to find that it actually needs to be 0.47. So you go into your next table right here. So we need to design at 57, so it's non-air entrained. And whenever you go in and interpolate, does anybody know what interpolating means? Yeah, you're calculating what it is in between two numbers. It's real basic math that I know in some of your physics and strength of materials class and a few other classes you're supposed to learn it. But it's in essence it's in between, and there's a real basic equation. You can Google it if you don't know what I'm talking about. If you have problems, I'll help you Google it. But so let's see now. So when you interpolate it in between the table, they got a 0.47 water cement ratio. So that's what actually governs. So step number, so just to kind of recap. So we figured out our design strength, figured out, okay, so for our durability, what do we need for our strength? So 4,000, great, that was the same thing as our design, but we need at least a durability factor of 0.50 for our water cement ratio. Well, when we went in to figure out what we needed to design for just strength, we actually found that our water cement ratio needed to be lower just to meet our strength requirements. So that's how we got our water cement ratio.
Do we have to do that on the test, or will it be given to us at the lower number? Will we have to interpolate on the test?
You need to know how to interpolate, but I may not. That is not what I'm going to quiz you over, but you need to know how to do it. So like for the homeworks, you'll have to. But I'm not trying to make it hard on you. But interpolation is real easy. Just learn it, because you're going to use it. If you're not already using it, you will. I guarantee it. So find the equation, plug it in. Some of your scientific calculators do it already. You just have to look at the function. So it is not hard. It's basic algebra. So step number 5, find the cement content. So we go in, we know that our maximum water cement ratio that we're going to be using is 0.47 from our strength. And so we can go to our table, and we know that the water content is 325 pounds. We found that in a previous step. So we can go through and say water cement ratio equals, weight of water divided by the weight of cement. So we plug and chug. So 0.47 was our water cement ratio. That was the maximum, that we had. And then we had 325 pounds of water divided by our, our X, our variable. So we can move our variable up, move our 0.47 down, rearrange the equation, and then come up with 691 pounds of cement. Step number 7, for course aggregate content, we are going to use a table to figure out, so if we have a fineless modulus of 2.8 for the sand and 0.68, 2.8 is our FM, so our fineless modulus of our sand. Going to go into this table. So 2.8 and then 1 inch for nominal maximum. So making sure I read that number right. All right. So they have, their answer is 0.67. So 2.8 for your finalist modulus with a 1 inch is 0.67. Yeah. And so what you do is that 0.67, that is 67% of the volume of the concrete is going to be coarse aggregate. Is in essence is what that table correlates everything to. Whether it's right or wrong or whatever is, is what people argue about. But that's what ACI 211 uses. So we will use that number. So 0.67 times your dry rotted unit weight, so 100 pounds per cubic foot, times 27. That's your conversion factor. So that's 1,809 pounds. So that's how they get their rock content. So now, we always use to find the fine aggregate content. We always treat fine aggregate as the filler. So we figured out everything else, our strength, our durability requirements, our, how much water, how much cement, how much air and coarse aggregate that is. So we know that we need to fill a 3 foot by 3 foot by 3 foot volume. So 1 cubic yard, we need to fill up a box that's 1 cubic yard. So we will use the fine aggregate as filler in this case. And so we will add up. So we have everything pretty much in pounds. So we had to convert everything. So, 325 pounds of water divided by 62.4, and that'll give you 5.21. Did the cement divided by specific gravity of 3.15 times the 62.4. So remember, you want to do this math and put that together. You don't want to, basic math. I know 62.4. You don't want to times that by that 691. Don't do that. You'd be surprised how many people do that. And they're like, why did I get this crazy number? That's way bigger than 27 cubic feet. Well, probably did your math wrong. Redo it. Air content. Remember, when you say air, whether it's 5% or 6% or whatever, that's percent of volume per yard. So, since you have 1.5%, you divide that into decimal times 27 gives you 0.41 cubic feet. Your coarse aggregate, we found 1,809 pounds. Take our specific gravity. We divide that by our specific gravity and our 62.4, our conversion. And we get out 10.82. So add all that up, and you get out with 19.96 for your volume, everything but not your sand. So like I said, sand's a filler, so you do 27 cubic feet divided by all the other materials that was in that volume. So that equals, yeah, you subtract it. So 27 minus 19.96, so 7.04 cubic feet. Then how to figure out your weight of your sand like you did the rest. Instead of, you just, same equation, but you flip things around, because you're, instead of converting from weight to volume, converting from volume to weight. So now it's, take that 7.04 times the specific gravity. In this case is 2.64 times 62.4. So 1,160 pounds. So this is the basic weight that we get from everything. So usually the total weight of concrete is going to be around 4,000 plus or minus, roughly 200 pounds normally. Your coarse aggregate content, usually it's somewhere between 1,600 and 2,200. Your fine aggregate content is usually somewhere between 1,000 and 1,400. But again, these are just general numbers. If you go up into Kansas City area, if you go up into Kansas, there's places where the sand's really coarse, and so those numbers may actually be more flipped. So they have a lot more BBs in their sand. So, and they have really small rock. So, but anyways, so when we talk about step 8, adjusting the moisture content of the aggregate. So what you can do is you can go in and do 1,800. So the moisture content, say there's free water of 2, then you can times it by 2, it's 2%, so 1.02, 1.06 to get your batch weight, or to get your changes in your water. And then so that basic water. And since the water absorbed from the aggregate will not become part of the mixing water, it must not be included in this adjustment. So instead of doing this, you can actually figure out, you can do the 1,800 times 2 minus 5. So the 5% is your absorption of the coarse, and then the 7% is your absorption of the fine. So if you remember, the absorption of aggregate is at SSD. So how much water actually gets retained into your rock or your sand, the pores, but doesn't have any free water around it. That's what your absorption value is. So the 0.5 or 0.7. So what they're doing is they're just trying to figure out the free water right here. So free water, the 2 minus 0.5 is 1.5% of free water, and it's the same thing with the 6 minus 0.7, which is 5.3. So that's how much free water that you're given. So they're saying, well, how much free water do you have? So they do the multiplication there on both of them to give you 27 pounds and 61 pounds of, that's how much free water is in there. So you can actually take your total water and you minus both of these numbers to get the actual water that you want to batch. Because whenever you go and you add in your rock and your sand, what that's going to do is you already have water that rock and the sand is incorporating into that mix. So you don't have to batch all your water, because if you do, then you have too much water within your whole concrete system. So you take out the amount of water and the amount of water for your rock and your sand. That's what this is doing. So when you go to batch per cubic yard, is you'll go in and you'll do 237 pounds of water. This is, your cement didn't change. And then your coarse aggregate and your fine aggregate is right there. So they did change. So whenever you do a moisture correction, so step number 8, adjusting moisture content, it's only for your water and your aggregate. Okay, so your air content's not going to change. Your cement, your fly ash, your admixtures aren't necessarily going to change. So step number 9, trial batch and test the actual mixture design. So when you trial batch, you want to make it lower. So if we want to design for a 2 cubic foot mix, then we need to take and convert all these. This is per yard. So we need to convert everything into 2 cubic feet. So 22 divided by 27, so 2 cubic feet over 27 cubic feet. That's how much you need for 2 cubic feet for water, sand, coarse aggregate, fine aggregate. So you batch all that out. So we'll have scales tomorrow, and you'll go in and you will actually batch out all those different materials per cubic foot or 2 cubic foot mix. And then you'll test it. So that's what we'll do tomorrow. So when you do your batch weights, that's where they're at. That way you have an accurate number. When in the past, whenever we've done a lot of our stuff, when we made concrete in the past, you know, the 1, 2, 3 method, it's like, well, how much, you know, you can go back and calculate how much volume that is, but it's not exactly super accurate. And it's hard to, you know, hit a target of 1 cubic foot unless you just go and do all the basic math, as opposed to, you know, doing 1 shovelful of each, you know, doing shovelfuls aren't as accurate. So this is kind of a little bit more of an accurate system. And then we'll just test. We'll do our testing. So these are all the different tables. So I will give this to you. And then I'm going to go through one more example problem. Because that's really typically, this is a little bit more typical of what I get whenever I'm designing a concrete mix. So they may say, Dan, Dr. Cook, need a bridge deck mix for ODOT. Okay, you know, I went through last time a class, you know, single A, what that is. So I may have a compressor strength of 4,000 PSI, and maybe I already have some data with a standard deviation of 50 PSI, sorry, not 55, 550. And then we want a slump of 5 inches. This is the minimum cement we have. I'm not going to do fly ash today. That's the only thing a little different. Obviously, specific gravity 3.15. And then we have a water cement ratio that's given, and then 6% air. And then these are some of the basic properties. So we're going to use a 1-inch nominal maximum size aggregate again. So the basic steps, like we just walked over every single basic step that was in ACI 211 through our lab. Well, some of this stuff we can kind of, you know, when they give you the cement content, you don't actually have to go back, or the water cement ratio. You just got to go back to check durability. And so in our case, you know, we may be just fine. And then our water content and our air, they already give us our air and our water, and we can just kind of calculate water from that. So a good first step, you should go through and you figure out how much you need to design, your actually required design is. So if it's 4,000 PSI and say there's 20 tests with it, and we have a standard deviation of 550 PSI, we're going to go to this table. It's 1.08. So that the corrected standard deviation is 1.08 times 550, so 594. And then we'll go and we'll take these two equations since 4,000 is less than this. We'll go through and figure out our safety factor now. So we go through the 594, we plug it through both of these equations, and we find out the 4,884 PSI is the one that governs, so you always pick the highest. And then we already had a 5-inch slump was what they required, so we don't have to use this table. We do need to check to make sure that our coarse aggregate size, the things, you know, the dimensions will look good. So I went through and, you know, found that, yeah, the biggest, the smallest one's this. So 1-inch nominal maximum size won't be a problem. So steps 3, 4, and 5 talk about how to do, you know, how to get your cement, your weight, your water weight, and your water cement ratio. And so for our durability requirements for the state of Oklahoma, they say 0.4H just fine. And so we can go through and go through a check with a point, you know, to figure out if this is fine or not. But whenever you go through and just to make sure for strength that you have a low enough water cement ratio, you find that you do. So we're just going to go with that same water cement ratio. We won't go through the actual table because that's, you know, we'll just go through and make sure we're good. So therefore, the water content, we take our 564 that was given times our water cement ratio that was specified, which is 270.7 pounds. So this is kind of where we're at now. This is the required cement, the calculated pounds of water from our water cement ratio and our given cement. And then I just converted it over to figure out the volume. To figure out the coarse aggregate volume, say we had a 2.7 was our example, and then we had a 1-inch, so we'd be in right here at 0.68. So that 0.68 number times your unit weight of your coarse aggregate, which was given an example, times your conversion factor of 27, gives you 1,891 pounds. So 1,891 pounds, we can divide that by 2.63 times 62.4 to come up with that 10.9. Great. How do we do fine aggregate? Well, remember, that's the filler. So we add up this column here, and we figure out, you know, minus 27. So when we do that, it comes out to be 7.27, and then we times that by 2.61 times times our unit weight to get to our 1189. So, you know, sometimes specifications can kind of simplify some of the stuff we're doing in mixed designs, but as you kind of plug and chug through some of this homeworks, it'll be easier. So I want to be very clear, our homework 2, or our homework that's assigned, isn't necessarily going through every step of ACI 211. We're going to have another homework assignment about ready to come out that goes over that. So I wanted to split these up so that you had 2 different ones. So it wasn't, first one was more theory, the second one's more actual plugging, chugging, and doing a lot more of the math.
I have a question about the adjusting to the moisture.
Yes.
We went over that on there. Are those percentages given, or is there a way to find those percentages when we're subtracting them out?
So we have our moisture that's given, and we have our absorption that's given.
Because you had the 0.5 and you had.
Yep. So for our coarse aggregate, we had absorption of 0.5, and our actual moisture that we measured was 2% for coarse aggregate. So if you remember in our first 3 labs, we went over aggregates stuff. And so whenever you go and you take a sample of coarse aggregate and you put it in the oven, and you weigh it before and you weigh it after, that's the actual moisture content. And then your absorption is if I take an aggregate and I put it in water for 24 hours and I come back and then I dry it out, if it's coarse aggregate or if it's fine aggregate, I'm gonna take a blow dryer and blow dry it out, just to make sure that, it's dry on the outside and but it's still, the water's still on the inside, and that's how you get those numbers.
Okay, so you did the 6 months to 0.7 and 2 months to 0.5, in the math?
Yeah, for the water. Yep. So that's kind of how they do that.
So there we go. Okay.
Yeah, and so a lot of this, you do some math to make sure, you have to run through the math and take your pencil and just crank it through, and that's what some of the homework will be, is just doing some of that in a way where I can still have it online, because that's what they don't want, paper. So a little different, but
I was just wondering where you got the numbers from, but since
Yep.
you stated, I saw so many slides, I forget what the public statement was.
Yep.
So, okay.
Yep, and that's why sometimes it's easier to have that given printed piece of paper up front, and then, as you're doing your math, you can, move other things by. But, and for the homeworks, a lot of times I may have I already have all that information right in front of you, so there's no confusion.
And you did, to get the final, you just did your H9. And you got the 1845 and the 1230. You did. Because you started at 1809 and then you dropped down, or you went up to 1845. Is that adding to 27 or?
Yeah, so this part here, this is what they do to say how much do you need to batch to get both your rock, to get your adjusted rock.
Oh, okay.
So, because you have 1809 is supposed to be when it's completely dry. So that's what they're supposed to design at, for ACI 211. It's actually, well, we'll just do that. Technically, it's supposed to be at SSD, but
So you're factoring the water content of.
yeah. So whenever you go in to do your batch, you don't batch 1,809 pounds of dry aggregate. You're going to batch, the 2% to adjust for your moisture content.
But you didn't take that out to find how much actual.
And this is how to figure out the water content. This part is. So this is how much do I need to batch? Great, I designed it, but whenever you go and you hand your design to a batch operator, how do I batch the concrete? And so this is, okay, well, your absorptions are this. So this is where you need to be at to batch the concrete. So that's kind of how they do that.
Okay.
If there's not any more questions, have a great rest of your day, and I'll see you tomorrow morning or tomorrow afternoon.